כבר לקחה את מה, עשיתם אותם?
כן?
כן?
השאלה היא ערובה? כאילו, זאת ערובה.
בא היום בשתיים.
היא באה היום?
איפה את חי?
את
לא רואה מה קורה פה מסביב?
לא. האמת שכן, ועשית טלוויזיה אצלך, אז כאילו, לא פעם אני כבר שעות עצמות.
לא, אפילו בלי טלוויזיה, פה מלא שוטרים.
באמת? וואו.
טלוויזיה, על הבוקר הסכמתי חולה באוטובוס.
רגע, אז לא, אבל באיזה שעה מגיעה? ידעתי שמגיעה.
12:25.
12:25. לא, השאלה היא, אז מתי הסגרו לי את
פשוט המזכירה שלו.
אז מתי הסגרו מה?
כי מתי אני
כל הזמן...
אין בעיה לצאת, היה לי כזה.
את בטוחה שזה?
לא,
כי הבנתי שתמיד
מה שדור שלי ככה מלכת כזה לגמרי.
אבל נראה לי אחרי 4... אחרי 4 אין לי.
כן?
בסדר, הפעם שעברה הוא היה באיזה 20 דקות. זה לא היה בסדר?
מה זה?
המשכתי איתך, זה לא היה בסדר?
היא גם אמרה שהיא מצאה לי כרטיס כניסה, ביום רביעי הבא.
מה שתגיד אני אעשה.
אוקיי, אז אנחנו נתחיל עם נעשה 3 הרצאות עם איזו הפסקה ביניהן, ואם יהיה זמן אני רוצה רגע לסכם לא רק את ההרצאות אלא את כל סורי. I'm so Israeli, you see. So the 3 students will present their work or the summary of 3 papers that are related to the issue of single neuron computation. And then if I will have time, I would like to summarize at least my view, but also would like to hear your view about what do you feel about the general problem here that we are dealing with is computation at the level of a network, whether it is the network, so to speak, that is essentially the major computational device as a whole, or are the elements of the networks, in this case neurons, synapses, dendrites, are fundamental, are important in terms of the computation that the brain is performing. So this is of course an open issue. There is no final thing to say about this, but you will hear the papers and then we can, I hope, we'll have time to discuss this particular issue. The individual versus the society. Okay, that's the issue. So.
So the article that I am presenting is named Wiring Specificity in the Direction Selectivity Circuit of the Retina, and it was done in the laboratory of Winfried Denk, and it was published 2 years ago in Nature.
Can you all hear? Because this time is without the sound. Is it okay?
Okay, that's worked before. Okay, so the big picture behind this study is to use new technologies in order to investigate how neuronal connectivity underlies neuronal computation, and they are doing that by focusing on the computation of detection of directed motion by the retina. Okay, so this is the area that we are going to focus on, and we are going to talk about 2 specific cell types in the retina. And the first cell is the ganglion cell, which is the output cell of the retina. It has axons that leave the retina through the optic nerve and into higher areas of the higher visual centers of the brain, like the thalamus and the visual cortex. And the other cell is the amacrine cell, which is an interneuron, and it is responsible for about 70% of the input to the ganglion cell. And there are about 20 different subtypes of ganglion cells and about 40 types of amacrine cells. So we are going to talk about 2 specific subtypes.
Can you turn off the light? This the one.
we're going to talk about two specific subtypes of these cells, and they are called direction-selective retinal ganglion cells and starburst amacrine cells. This is a photo which is a reconstruction from an image of an electron microscope, and the yellow circle, the yellow circle in the middle is the soma of the starburst amacrine cell, and we can see that it has a star-like shape of the dendrites around it, and the two green ones are the direction-selective ganglion cells. Okay. So up until 50 years ago, there was a common belief that direction selectivity is generated only at higher visual centers of the brain. And in 1963, Barlow and Hill discovered that it can actually be generated in ganglion cells in the retina, and these cells are called direction-selective retinal ganglion cells, and they respond to a specific direction of motion, which is called the preferred direction, but they don't respond to the opposite direction of motion, which is the null direction. And one possible explanation for this functional asymmetry, and by functional asymmetry I mean the response only to one direction of motion but not to the other direction of motion, is enhanced inhibition while null direction motion. And the main source of inhibition to the ganglion cells are the starburst amacrine cells. So that is why it was proposed that the starburst amacrine cells are responsible for this increased inhibition during null direction motion. Okay, few words about starburst amacrine cells. The first important thing is that these cells have no axons. So these cells...
Axon with the A.
Oops.
Axon is something that has to do with genes.
Okay.
So axon.
So axons, sorry. So their output unit is the distal part of their dendritic branch. And another important thing that was discovered also in the laboratory a few years ago is that the dendrites themselves are direction selective. So they are activated by motion from the soma towards the dendritic tip, but they are not activated by the opposite direction of motion from the dendrites into the soma. Okay.
Motion, you mean motion inside the cell? Not motion...
No, I mean stimuli that moving outside and creating an image on the retina. So
Can you go back? Because this is I don't know if you already met a neuron without an axon. So that's something we should be aware of. In some cases, this is a case of a nerve cell without an axon. So that has to change a little bit your view of input-output relationship sometimes in some networks. In this case, both the input and the output are from the dendrites. So there is no axon. So dendrites are receive input from presynaptic elements like the bipolar cells and other amacrine cells, but they generate an output, inhibitory output mostly, from the dendrites as well. So there is a local within local dendrite that receive input synapse and generate output synapse inside a small compartment of the dendrite. Is that clear? Sorry? Doesn't need to the soma. It gets to the soma just because there is voltage distribution, but it could be very local. You get a synapse here, you get an output there, and the soma doesn't know anything about this local processing. So that's a unique type of cells.
I don't understand exactly what the direction selectivity is.
That's for you to describe.
They respond if you move stimuli in a direction that is from the cell body out, then the dendrite will be activated. If you have the opposite kind of motion, then he will be activated. And this motion of light,
motion
of
outside.
bar light, yeah, you do it on the retina, and you get the image, the dendrite. So you can look how the dendrite is, what is the structure of the cell, and to what direction you see the dendrite pointing. And you see that this cell is only activated if you have a light that moves in that direction. But not if you have something that's spreading, expanding, but
from
not
the soma out,
Mhm.
from the center out, let's say in this direction, this right 45 degrees dendrite will be activated, and in the opposite direction, from the tip of the dendrite inside the soma, 45 degrees, so 200 and whatever, 325 and so on. This direction it will not be activated. Per dendrite.
But the other
Not the neuron, the
dendrite.
dendrite is not good.
The dendrite.
Yes.
Yes.
And it will be, I think, clearer if I continue. So I'll come back to this point later on. And this is not even the study that I'm talking about. Okay. So we said that we have one possible mechanism for the direction selectivity in which we have enhanced inhibition while null direction motion. And that we said that the stabile cell may be involved in this inhibition. But we still have some open questions. For example, is this asymmetry due to increased synaptic conductance, or maybe it's because we have more synaptic contacts? And another question is, does it depend on the location of the stabile cell soma, which is one proposal, or maybe it's more connected to the location of the dendritic branch of the stabile cell. And these two questions are difficult to address by solely physiological means, and that's why structural information about the location of individual synapses and about the direction of the dendrites is needed. Okay, so this paper is referred to as the technical tour de force, and that is because it uses two very different microscopy methods. And the first one is a functional analysis, and they use two photon microscopes to simultaneously visualize the retina and to monitor calcium activity, which is a signal for neuronal activity. And by that means, they identified the preferred direction of the ganglion cells. And the other method is a new electron microscopy method, which is called serial block phase electron microscope. And in this method, it enables the researchers to get a three-dimensional volumetric image of the tissue. And they do that by repeatedly scanning the surface of the tissue with an electron beam. And after each scan is done, they have a very sharp diamond knife, which is this one, and that slices a very thin slice from the surface of the tissue. And they do it repeatedly, so they get a three-dimensional image of the tissue. And this method has two big advantages. And the first one is that it has a very good three-dimensional resolution that enables the researchers to trace very thin, densely packed dendrites in the retina and to identify individual synapses. And another big advantage is that it is completely automatic, so you can study relatively large pieces of tissue.
Just one little comment. One big advantage of this technique is because you cut it from above, so to speak. You scan it from above and then you cut it. The issue of alignment becomes simpler, because you see it stands on the same location, and each time you cut a piece, and the next one is, if you photograph from above, it remains one on top of the other. That helps this stacking one on top of the other. Otherwise, if you would be set like you did in the old way, you separate it, and then you have to find how to align each section to the other one. So that's one aspect of it. Just to give you numbers, I don't know if you know what is. Do you know what is this? How thin?
It's
The order. How thin is an electron microscope slice? Because this is synapses, otherwise you won't see. So do you know something about the...
Yeah, I think it's 25, it's 1,000 of the thickness of a human hair.
Of a what?
Of a human hair. That's what they have in the... And I haven't done, I
Yeah,
think...
so, yes, so it's in nano, it's about
Yeah, I think 25.
20, 25, now
25
today it's into 10 or 15 nanometers. Depends on whether 1 minus. So it's, you know, 1,000 less than, so the light microscope is in micrometers, yeah? The order. This is nano, so this is a million more thin. That's the level we need. That's why you need so many in order to reconstruct the whole piece at the level of synapses. Because this is, you know, very, very thin one. So you need many, many millions to reconstruct the brain. But we should do it soon. Okay.
Okay. So, what did they do? They took a dark adapted retina from a wild type mouse, and they filled it with calcium indicator, which is a calcium sensitive fluorescent dye, and then they imaged it in a 2-photon microscope while stimulating it with bright bars, bars of light moving in 8 different directions. So we have here the 8 different directions of the stimuli, and the calcium indicator indicated in response to which direction of motion there is a calcium flow into the cell. And so we can see here each row here is 1 ganglion cell, and we have the summed reaction of this cell, of these 4 cells here. And the black line represents the preferred direction of each one of these cells. The direction that this cell responded the most. And they are color-coded by 4 different preferred directions. So these 4 cells represent the 4 groups of all the ganglion cells, and they divided all the ganglion cells into these 4 groups with these 4 preferred directions. And this little circle is the map of the 4 preferred directions, and this also will be on the next slide. So we need to remember that this represents the 4 preferred directions of the ganglion cells. And you can see here, this is a photo from the 2-photon, this is a 2-photon image, and we have the cell bodies of the ganglion cells, and again they are color-coded by these 4 colors that represent their preferred direction. And this is the same image, just in the serial block phase electron microscopy volume, so we can see it has, it's a 3-dimensional image. Okay. So after they identified the preferred direction of the ganglion cells, they chose 6 of these ganglion cells, and they wanted to trace their dendrites. And they did that by tracing their skeleton in the center of the dendrites. And by that they identified all the dendrites of these 6 direction selective ganglion cells, and again they are color-coded by their preferred direction. And then they wanted to identify the synapses between these cells to the starburst amacrine cells. And they did that by looking for a specific geometrical shape that is very characteristic to this kind of synapses, when you have the presynaptic dendrites wrapped around the postsynaptic dendrites. And you can see it also here in the electron microscope image and in a 3-dimensional model. So after they identified all the synapses that look like that, they traced the presynaptic cell back to his soma, and then they did again the skeletal reconstruction of all of their dendrites. And by that way they found 24 starburst amacrine cells that are connected to these 6 direction selective ganglion cells.
You understand how terrible work it is.
It seems like it. It's pretty.
It's pretty, but it's very hard.
Okay, and the next step was to identify the specificity of the synapses. And they did it once from the perspective of the ganglion cell. So this is one starburst amacrine cell, and you have this circle. The black circle is his soma, and the black lines are his dendrites, and they color-coded all the synapses that this cell has with the 6 other ganglion cells by the preferred direction of the ganglion cell. So this is the map of the preferred direction of the ganglion cells. And we can see that the synapses are located on dendrites that are in the opposite direction than the preferred direction of the ganglion cell. So what do I mean? For example, if we look on the yellow synapses, they are located on dendrites that are pointing upwards, but they are connected to the ganglion cell that has this preferred direction. So the synapses are actually in the null direction of the ganglion cell. And that also brings us back to what we said about the properties of the dendrites of this starburst amacrine cell. That
what are these black spots?
The black spots are all the synapses of this starburst amacrine cell, and the colored one are the synapses that this cell has with the ganglion, with the 6 specific ganglion cells that they are looking at. So of course we have unmapped.
Could contacts for other ganglions that are not part of this.
I'm coming back to this point at the end. Okay, so for example.
You should ask question, not me.
So if we have this direction of motion, we said that the dendrites with the yellow synapses will be activated. That means that this cell will inhibit the ganglion cell, so that is connected by these synapses. So the ganglion cell won't be activated towards this direction of motion. But if we have this direction of motion, then these dendrites won't be activated, and the ganglion cell that is connected by these yellow synapses will fire to this direction of motion. Okay. And that's the most important thing of that, yes.
The color codes arbitrary, or is there really clustering around 4 different directions?
No, it's these directions. This map.
I suppose there's some continuum.
Yes, there is a continuum. What they did at the beginning, here, they had 8 different directions, and then they clustered all and they had the summed reaction of each ganglion cell to these 8 directions, and this summed reaction you can see by this shape. This shape represents the sum of the reaction to these 8 different directions of motion. And then they had the summed reaction of each cell, and they had one vector which represents the mean activity of the cell to the preferred direction, and then they clustered the cells into 4 groups, represented by these 4 directions.
So maybe there's someone in the purple group that is very close to.
Yeah. Also, you can see here when you look at the synapses, of course, that it's not very the clustering also here on the location of the synapses is not sharp. So they chose to look at these 4 directions. Okay. And you can see exactly the same pattern also if you look at all the starburst amacrine cells and all of the synapses. And again, they are color-coded by these 4 directions. You can imagine that all the cell bodies of the starburst amacrine cells are in a pile, one on top of the other, and these are their synapses. So you see the same pattern, that the synapses are located at the null direction of the ganglion cells that they are connected to.
So this is one and this is
Yeah, this is all the 24. Okay, and they did the same thing from the perspective of the ganglion cells. So here we have in the middle, the gray circle is the cell body of the ganglion cell. These blue and cyan circles are the cell bodies of the amacrine cells. And what's important are the smaller circles, which are all the synapses. And they created a line that is pointing from the location of the cell body of the amacrine cell towards the location of the synapse. And this line actually defines the dendritic angle of the dendrites of the starburst amacrine cells. And you can see here, these are polar histograms of these dendritic angles. So, for example, if we look at the cell that is here, we see that most of his synapses are pointing to this direction as the arrow. And this cell is represented by this polar histogram. So they are the same cell, and the black triangle represents this direction of the synapses. But we can see that the preferred direction of this cell is the opposite direction. So it's the same pattern as we've seen before, and actually they found that direction selective ganglion cells receive 12 times as many synapses from the null side than from the preferred side. Okay. So to conclude what we've seen, direction selective ganglion cells tend to receive many more synapses from starburst amacrine cells dendrites that are oriented along the null direction of the ganglion cells. And that implies three things. First, direction selective ganglion cells acquire their direction selectivity by predominantly collecting starburst amacrine cells input that inhibit the activation of ganglion cells during null direction motion, which is what we've seen with the yellow bar moving up and down. Development of asymmetric inhibition arises, at least partly, from changing in the number of synaptic contacts, because we've seen we have a lot more synapses in one side than the other. And the mechanism that I have here also some kind of mistake, that determines whether a synapse is formed uses the local dendrite geometry or activity. Okay, and the main thing that this article tells us, and the main point of the article, is that structural asymmetry can sit at the basis of functional asymmetry. So this is the main point of the article. In this specific case, we can see that the wiring specificity, which is the structural asymmetry, can contribute to the computation of direction selectivity, which is the functional asymmetry. Okay, some open issues and comments. So, of course, that doesn't mean that this is the whole mechanism that is responsible for direction selectivity. And for example, there can be also increased excitation while preferred direction motion. So the same starburst amacrine cells has also, they release two kinds of neurotransmitter, GABA, which is inhibitory, and acetylcholine, which is excitatory. So there can be also some kind of a push-pull mechanism which enhance inhibition during null direction motion and enhance excitation during preferred direction motion. And another point which connects us to what Idan said about the synapses, that not all the synapses of the starburst amacrine cells were mapped. We've seen all the small black circles, which are synapses that we don't know which cell they connect to. So, of course, that some of them can be connected to other ganglion cells, but some of them may be connecting between two starburst amacrine cells. And that also can be related to this direction selectivity mechanism. And of course, that for these issues, we need further research. But again, the main point of study is to show us an example how otherwise difficult neurobiological questions can be addressed by combining physiological means by structural research. And that's it. Thank you.
Question? So I will start. First of all, one question would be, suppose I don't have these complicated connectomics issues and I don't have a microscope and all these other things, but I can record from the ganglion cell. I can record from the ganglion cell intracellularly, and I can, I guess, under voltage clamp, let's say, I can see that in one direction I get more inhibition than in the other. Just by the recording, yes, I just see that when I move it in the null direction, I see more inhibitor, more IPSP, larger IPSP, or IPSC if I do voltage clamp, and if I do it in the direction that is preferred, I see less inhibition. So that on its own, without doing all this connectomics, tell me that there must be some role of asymmetry in the inhibition, just from recording of the postsynaptic cells, of the classical neuroscience. So, do you agree? That's already there, I can see that there is...
We can see that there is asymmetry in the function of this cell, but we don't know why it is. And that brings us to the first two questions that I showed. For them, we need, if we want to see if maybe that we have more synapses, and maybe we have more synapses only in one direction of the cell, but not in another direction of the cell, we have to combine the functional research with some kind of structural analysis.
Because there were hints already before, as I said, hints that there is this asymmetry in terms of inhibition, just because of the recording starting point. Then the question is, what is the origin of this asymmetry? Who is doing this asymmetry, so to speak? And this new paper shows that this is this asymmetry in connectivity. So that's one question. But the other question, which is more difficult, I think, for them, is that the directional selectivity is already computed presynaptically. You can see already the presynaptic cell, this cell, is already directional selective. So, in terms of computation, you ask me when, what level, maybe levels, yes, because it could be done in a sequence, so to speak. We know one thing, that the receptors are not directional selective. The receptor itself is just looking at the world. It doesn't care if it goes through here or through here. So there we know the first stage is not directional selective. But at which stage the directional selectivity emerges, they showed us that it's already at the level of amacrine cells. And so the question is, how do the amacrine cells become directional selective? And this, of course, they did answer. They just show that it is directional selective, but we don't know the mechanism, because we have to go one step backward, yes, to the bipolar cell, and us are a bipolar cell, so we don't really understand the system. We just understand the end result, but we don't really know how it is computed. It's just an important point, that eventually when I say I know how the retina computes direction of motion, I know now only some of it, just the postsynaptic final stage before the output to the eye, from the eye to the thalamus, but I don't really understand the network effect as yet. So that's an important issue to know.
Why do you need to go one step back to the bipolar? Can it be just in the dendrites of the amacrine cell?
Yeah, it can. I don't know. I just don't know. It could be that that's the first time that you compute. And then you have to understand the mechanism why the amacrine cells are sensitive to direction. Or maybe it is already computed in the previous one.
They have also another research from, I think, 2007, in which they blocked inhibition to the amacrine cell from different types of cells, and then they saw that it's only in the dendrites in which they do these computations.
Right. That's another thing.
Students first.
What kind of animal were these cells taken from?
These from a mouse.
Mouse.
Yes, it was a wild-type mouse.
Is it important that all the yellow synapses are clustered in one dendrite? If the finding would be that they are distributed all over the dendrite. Would that
Ah,
make sense in any way?
when you say clustered, you mean at the top part of the dendritic branch?
Yes. Let's
Because
say
they
the
are
finding was
outputs.
that all the yellow synapses would be distributed all along the dendritic tree. Would that be possible?
I'm not sure I understand your question. If you mean just one moment. Okay. If you mean here or all over here, or if you mean here and or all over here.
All over, yeah, the second
Oh,
part.
the circle.
Yes.
Then that would be. Oh, the main idea is that their direction in space is in this direction. So they are located mostly here and not all over here. If they were all over, then the idea of the location on the dendrite and the orientation of the dendrite wouldn't matter.
This has implication on dendritic computation.
Yeah, the idea, and that was one of my points, that the synapses are connected to the geometry of the dendrite. We have more synapses that are located here at this angle of the dendrite. So they are influenced by the geometrical properties of the dendrite, and that is why functional analysis is not enough to know that.
Especially if you record only from the cell body, then you would not
Yeah.
know, because it is done locally, especially in this case. The cell body will not tell you anything
Yeah.
on what is being done locally on the dendrite, because there's exactly this local interaction between this tip of the dendrite, which is sensitive to this direction and not to this direction, is the output to the next cell, to the ganglion cell, and from the cell body you have no preference in that sense.
Yeah,
The
they
cell body
showed.
will get all the directions.
They showed that if we do the stimuli that I showed you, if we move this stimuli in this direction or in this direction, you can see changes in the activity only in calcium in the dendrite, but you don't see it if you look just at the voltage of the soma.
Yeah, so this is really built from subunits. Many
Computational
subunits, and not
subunits.
only four, because many directions are there, and each subunit is locally computing direction. The cell body is just supporting them, but it's not involved with the computation. It's a very particular cell type. It's very broad, it's very big also. So it occupies a huge space in the retina.
I don't know if this question is discussed in the article, or maybe it's a question for Dan. But I just wonder if they talked about how can we apply these findings to human beings. And I just remember that we talked two weeks ago about the enormous difference between the V1 of a cat and the mouse. The fact that within the V1 of a cat it's within columns, and the organization is totally different within a V1 of mice. And I just wonder, in these kind of researches, how can we know what do we have to do with that? I mean, what the human being has to do.
In terms of this computation, yes.
In terms of this structure, can we know that if it's organized like this in mice's retina, I mean, can we know איך אנחנו יכולים להכליל את זה?
You take a retina of a human.
So you know.
And you can do it. It doesn't,
like a dead tissue?
First of all, you can take a dead tissue, yes. So you can't record directional selectivity and so on in the dead tissue, but you can characterize synapses in the dead tissue. At least you can see whether there is. I can tell you that we have amacrine cells and we have ganglion cells and so on, but whether this geometry applies also to humans, this was never done. So I don't know how general this rule is for all mammals. This we don't know, but in principle, at least anatomically, you can do connectomics to a dead brain.
We
and characterize synapses and cells. Activity is something else, because you don't know which direction is this ganglion cell when it's dead. So you have to do some kind of analysis.
But you told us you can do it with binary from the
From the cortex.
surgery?
Surgery.
Yeah, but not from the retina.
This was from the cortex. You don't take retina usually. Yeah, so this is a general problem about doing experiments with humans and getting, okay, so that's a general issue. But this is for mammals, and this is for rats and for cats, and for monkeys. It was not done. This is the first one.
Years ago was on rabbits.
Rabbits, yes, rabbits.
applies to humans. No.
You can ask more difficult question. What about optogenetics and rainbow and all these techniques? What to do about humans? You don't make humans fluorescent, and all that.
Yes.
Let the society to decide what is important to do or not. Okay, good. Any more questions? Because we have. That was very good. Thank you very much. So, what's next? אתם רוצים לעשות סוג הפרק או מה? Yes, you can decide. We can make it traditional. We have two more, so it has to be about 20-25 minutes of 10-minute discussion. So don't do it. We can stop here, but this will mean that we will end it too. We can stop. I don't know. Is it a long one or is it a short one?
Short one, supposed to be.
So let's give the grant to drink water or something like this. Correct.
וואי, אתה ריכזת נורא מגבוה. ממש טוב.
מישהו יכול לעזור פה עם
יש מישהו שמבין
מה הבעיה?
המחשב של הלאומי לא יכול להתחבר כנראה.
אז צריך לחבר את זה.
המחשב שלך לא
כן, זה
מתחבר.
גדול מדי בשבילו. יש לו כאילו
קונקטור אחר, ואין לך את הדאפטור?
יש לי.
אבל
אפשר אולי לחבר את המחשב שלה?
תהיה, אתה מבין?
מה החברת שלי?
אם יש לו את זה עדיף.
אבל אתה צריכה, יש לך פתאום. אוקיי, אנחנו עושים הפסקה. כי יש כאן בעיה של הדאפטור וכך הלאה. ניקח 5 דקות, לא יותר, כי יש כאן בעיה של הטלפון. יש לה מחשב עם הדאפטור, לא יודע. אתה לא יכול להתחבר. אבל אתה חייב דאפטור לקחת.
כנראה, לא ידעתי.
לא, יש שם בצד השני.
אני לא מכיר את הכלי הזה, אני תמיד צריך לדאפטור. אבל זה בא עם הדאפטור? זה לא בא עם הדאפטור?
לא, בסדר, אני רוצה לברר אם
זה HDMI הדבר הזה.
זה עלה?
כן, איפה הקליקר
יש
הזה?
לך את זה מוזר, לא ראיתי בחיים שלי כזה בלי...
הקליקר?
אז יש פתרון לדנדריטי קומפיוטיישן והניורונים של קונר?
לא. אני רואה שאני מקבל את כל הסולט and pepper, את כל ה-rotation בניורטים. בסוף יש אוריינטציה אחת שהיא מועדפת. ואין לנו שום מושג, כי הוא רשם את זה די משונה, מספר מאוד קטן, אז אני לא יודע מה...
אבל פה יש אתה שיכול להגיד גם מפה, גם מפה, תגיד מה פה.
גנדי, העמקרית, אבל הם מדברים עם גנדים ואחרים. זאת אומרת, הדנדריט הזה מדבר עם העמקרית.
כן, לא, זה
אבל שם מיפו.
זה שמיפו לגמרי, את הסטרקצ'ר פונקשן, זה באמת מקבל קלאסטר מכולם. כן, עכשיו כשזה סולט אנד פפר, בסוף יש לו אאוטפוט אחד.
שאלה פתוחה. לי סטודנט שעובד על זה, בדיוק על זה, כן? איזה סוג של חישוב מדויק
אני
יכול לעשות?
מנסה לראות איך הגיאומטריה הזאת
כן, כן. תראה, אם היה להם יותר נקודות לקולות, אז הייתי יכול להגיד למשל, שזה אולי בסך הכל הרבה יותר, נגיד שהיה לך מתוך ה-5,000 סינטות, 4,000, הם היו באוריינטייז הזה, וכל השאר בכל בית הספר, אבל פעם קטן יותר, בדיוק, אז זה לא חשוב, אז אתה עושה לג'וריטי. אני לא יודע, מה קורה שם, זה יכול להיות זה, שפשוט המג'וריטי קובע, הרוב קובע. אולי יש שם איזה משהו לא ליניארי שמגביר זווית אחת ולא אחרת, זה כבר קטע מסוים. אין לנו אינפורמציה. זה סוג השאלות של הסיפור הזה. מה יכול להיות?
יש אנלוגיה בין ה-structure function concept של single cell לבין רשת. גם שם יש דיבורים כאלה. אתה מסתכל על direction של concept, אז כל ה-pinwheel והמקובצים ככה כמו ה-sound
כן. הפינוויל זה גם מיוחד, כי הוא יושב בדיוק בנקודה הסינגולרית שהקיבוצים שלו גם לא יוצאו. כי הקיבוצים שלו פועלים בדיוק במקום הזה. אבל...
התנאים שיושבים בתוך פשוט מדהים אותי האנלוגיה הזאת בין על הדנדרית, הסינגל סל לעומת המאפ הכללי שלו.
צריך לדבר על זה. לא חשבתי. רגע, כולם פה כבר, אפשר להתחיל? Let's start. We start now. Okay, you have to start, otherwise we are not going to make it on time.
I don't have a problem to skip the question part.
Oh, the question part you don't want... Okay, no question. Fast without question.
Okay, so I'm going to talk about the role of dendrites in the auditory coincidence detection. And this article was published by Edmond Smear, Carr and Rinzel in 1998 in Letter to Nature.
Your name again?
My name is Michal.
Michal, sorry.
Okay, so as we heard in the last 3 meetings, there are a lot of kinds of neurons with different dendritic trees, and we assume that these dendrites have some computational importance, but until this article was published, there was no evidence of the advantage of this dendrite computation to the function of the neurons. So the purpose of this article was to find a specific system, a specific neuron with a known function, and to find out how the dendrites computation can help the function of these cells. So the system that they chose is the coincidence detection neuron. These are neurons in the auditory system, in the brainstem, and their purpose is to find out the location, to decode the location of a sound in space. So as you can see here, this is our... Okay, so you can see here if the sound is located in the middle, so it gets to both ears, the left and the right, on the same time, and then there's some delay mechanism that makes the sound get to the neuron at the same time, only in this neuron, and these neurons get the sound in different delays. So this neuron will fire, and this neuron will decode the place in the middle. And when the sound comes from here, then it will get faster to the right ear than the left, but there will be a longer delay for this neuron, so this neuron will have a coincidence detection. All of these neurons fire when they get the information from left and right at the same time. So this structure allows these neurons to decode the different place on space. So this is the function of this system. Why choose these neurons? First of all, they have a stereotypical bipolar dendrites. So this is the axon, and these two are the dendrites. On the top, the
chicken, and on the bottom it's for humans, but both of them have just from the soma two dendrites, and inputs for each dendrite come to a specific from a specific ear. So this one gets the input from the left ear, and this from the right ear. And another benefit for this neuron is that the electrophysiology properties of them is well characterized. So we know how they act and in different voltages, in different electrophysiological conditions. And another important point is that the length of these dendrites, as you can see here, is changing as a function of the frequency that they decode. So for neurons that react to high frequency will be shorter, will have shorter dendrites, and neurons that react to low frequency will have longer dendrites. So this is something that they will also have to explain in their model why is this so. So this is the system. First of all, they use a point neuron model, the one that was that doesn't account for dendrites, and indeed they get the same electrophysiological properties as in the real neurons, and they get this graph, which is a very important graph.
When you say they get, you mean that they build a model, a nonlinear model, Hodgkin-Arctic type model, to replicate the nonlinearity they record in the cells. Is that what you're saying?
No.
When you say they get, what do you mean they get?
They
This is a model.
Yes, they model voltage, and they see how the model produce what it produces. If there's an action potential or a hyperpolarization.
So they build a model. They build Hodgkin-Arctic.
Yes, they took all this. I have it in the.
No, just explain what we see.
Okay, so they built a point neuron model with all the conductivity and the channels and pretty standard one, and they get the same thing as in the real cells, and they get this graph, which is a very important graph, which means that sound comes in waves, and if the sound on the same time from both ears, then they will have no phase shift. They will come at the same time, and then the firing rate will be maximal. But when the sound comes not on the same time, so there's a shift, there's a phase between both ears, and then the firing rate will be minimal. For the as big as the phase, the minimum the firing rate will decrease.
Is that clear? They replicate the sound, the difference in sound.
So this is how the neuron decodes the coincidence between right and left. If the right and left comes together, then it will have a maximal firing rate. If they are coming completely not together, then it will have a minimal firing rate. And the purpose of
not
the
together in time, you mean?
yes, the phase
simultaneously or not simultaneously?
Yes, if they are coming, if the phase of the wave is the same phase or there's a difference in this phase. Both of them are coming. If this is one cell, so the other cell can also wave, yes, and it can also be that this is completely different. Here is the minimum, and here is the maximum.
This is not video others.
This is a zero phase. There's no difference between the maximum phase here and the maximum phase here. And this is 180 because this is the maximum phase and this is completely the opposite.
The 0 degree is exactly in the front of the skull of both ears, right?
No. It's for a specific neuron. The system is built so that it will detect the information coming at the same time. But even if it's not in the middle, so this neuron will react when it's in the middle, but this neuron will have the phase 0 when it's not in the middle, when it's on the side. So the structure of the system is built so there's a delay, and all of these neurons will react when information information from left and right will come together. And the system built this way that this neuron will get the information together when the source of the sound is in the middle, and this one will get the information together when the source of the sound is there. So both of them functionally detect when the input from both ears comes together, but each one of them decodes different places in time, in a space. Okay?
No, you don't understand.
I just wonder what's the difference between the 0 degree and the 180 degree.
So
the 0 degree, I understand that it comes from exactly from the middle in front.
No.
And the 100.
No. So the degrees are not of the place in space. The degrees are the differences in the wave of the sound.
In time between the dendrites.
Okay. So this is an important point, that this is how the cells function, and if we can get the difference between the maximum rate and the minimum rate even bigger, firing rate even bigger, then then the cell will be able to detect better. It will function better. Okay, so now they used the same model as before, but they added it to dendrites. So how did they add it to dendrites to the model? They just added an axial resistance and split the inputs. Instead of coming to the soma, they split it 6 input to left side and 6 to the right. So this is the bipolar neuron model for modeling the dendrites, and they simulated the input for these inputs to come exactly at the maximum phase. Okay, so this is the phase of the sound. And indeed, they got so this is the same graph as we saw before, the firing rate as a function of the phase. But here we can see this is the point neuron, which is the dashed line, and this is the bipolar neuron, which is the continuous line. And you can see that the continuous line has a bigger difference between the maximum and the minimum response, which means it functions better. It can detect better between phase of 0 than exactly the opposite. Okay, so this result is for a specific maximum frequency for 200 Hertz, but they also calculated it for a variety of frequencies. So if we look at all kind of maximum frequencies, then this is how the point neuron will react. This is how a thick bipolar neuron, and this is a thin bipolar neuron. So a thin bipolar neuron will react even better. Okay, we can see that if we are, let's say, like here in 200 hertz, then here the difference between the max and the mean, 220, it will be 180. But if you take the bipolar neuron, then the difference between them will be bigger. The difference between them, it will be 190, let's say, and for the thin one, it will be even 200. Do you have a question?
Just a bit confused. So is it the firing rate or the frequency of incoming?
This is the firing rate. Okay, this is the maximum firing rate, and this is the minimum firing rate. Okay, so you have different firing rates of different in the model. You can different firing rate, and then you can check how well is your cell doing, is your model doing in these different firing rates. And we can see that it's doing better in variety of firing rates, and it is even better when it's thinner.
Maybe a very stupid question, but how the brain differentiate between minus 180 degrees to...
It doesn't. It's the same thing.
So how do...
It's the same spot. Minus 180.
From here to here is the same spot?
What? From the different sizes? No, we can go back to it will be a different neuron. that will get so this 180 is
If my minus, this is the same case for my minus plus?
This is the
same
phase
case
shift
in
of the sound,
nature?
not in phase. The phase
Okay, but
shift.
this is the same case in nature. This is the same stimuli of the 2 minus and the plus.
Again?
This is the same stimuli or the mirror image of the stimuli?
This one? This phase?
Minus and plus. Minus 180 and plus 180. This is
the same. It's the sound that gets to the ear and the phase.
So you can cut the graph. It's actually
yes.
the same.
Yes, that's what it's saying. Because this is how sound works. It's waves.
The period, right? The period between.
No, because if I thought that the plus presents that here is the maximum and here is the minimum, for example, and the minus represents
no, but it's not maximum and minimum in space.
Okay, the maximum that of the wave
okay.
that come to the right here, for example, and the maximum and minimum here, and the minus represents the opposite. So how the brain differentiate between two cases?
I understand what you're saying. Because it will not come. The system is built.
Well, I think this one is zero when you have maximum here and minus 180. I don't know.
But I think this is because of the other neurons around, no?
Yes, so this neuron will get the coincidence when it's here, and this neuron will get coincidence when it's here. It's not the opposite, because this will have a delay and it will come in a phase, and this will not have a delay and it will come at zero. So the 180, the maximum is exactly the opposite side. Okay, so why is this happening? Why do we see this phenomena? So we can see this phenomena because of the nonlinear summation of the input in the dendrites. Okay, so if we have a point neuron, we need to decide of threshold of, let's say, 6 inputs is enough for this cell to fire. So if I have 3 from this ear and 2 from this ear and 3 from the other ear, or 4 and 2, I will get an action potential. But also, if I have a very high stimulus in one ear, only 6 inputs only on the right ear, then this point neuron will fire. When we have a formation on the dendrites, then if all the information comes from one ear, then all the information comes to a specific dendrite, and the formation is non-linear. Okay, so the dashed line is the blue line is the linear summation. So we have less than threshold. The sum of them is not above the threshold, and we don't have an action potential. But if we get the information from both of the ears, then we get here there's a nonlinear formation, and here there's a nonlinear formation, but these two dendrites summate together linearly in the soma. So this is not exactly linear. This is not as the blue line, because here there's nonlinear formation in here, but the sum of these two is above the threshold. So this is the mechanism that allows these cells to detect better using dendrites than only points.
But let me say it in my words, okay? If you have all the 6 synapses coming to only cell body, suppose you have only a cell body, and it doesn't matter if it's 3 from the left ear and the 1 from the right ear, if there is 6 synapses, 6 input coming, you will fire a spark. Okay, you don't know if it's 3 from left, 3 from right, or 6 from one, or 6 from the other. You know that it's 6 is enough to fire, if it's a cell body only. If it's dendrite, if the input comes to the dendrite, let's say that you have 6 from the right, let's say 6 synapses are coming to the right dendrite from the right ear. Then, because of this sublinearity summation, that's the assumption here, the 6, if they are local of the dendrite, the 6 will sum highly non-sublinear. This is the red here to the left, yes? Okay, so the dendrite suppresses. The dendrite doesn't like the case, so to speak. It doesn't like the case where you have a lot of excitatory synapses localized because they cannot sum up in the dendrite. They cannot sum up because of the saturation effect. So locally you get sublinearity, strong sublinearity. But if you take the 3 here and the 3 there, it likes it better. It's still nonlinear because 3 are not 1 plus 1 plus 1. So it's still nonlinear per dendrite, but much less nonlinear. So 3 and 3 is better when you have dendrite than 6 when you have only one dendrite. So that's what the dendrites are doing here. They suppress too many coming from one ear. And so they make a distinction between 6 to 1 or 3 and 3. And the solid body cannot do this distinction. Okay? So that's my way of thinking about it. So the sublinearity which makes the computation here, the fact that you sum nonlinearly, these are passive dendrites. So, because if it was an NMDA synapse, the whole mechanism will not work anymore.
Okay, so this graph actually shows the calculation for different inputs to the left and to the right. Okay, so we have okay, so these lines are the threshold for firing an action potential. Whatever is above the line will create an action potential, and an input that is below the line will not create an action potential. So they showed the threshold, how does it look in different, in the 3 different, 2 models, but 3 different neurons that they created, and you can see that when when we have a point neuron, it's totally linear. So GL plus G right will get the threshold. Okay, but if we use a dendrite in a model, so it will become nonlinear, and they calculated some indicator for this nonlinearity, how nonlinear is our neuron. So for this is a parameter which is between 0 and 1. If it's alpha equals 1, then it's totally linear. This is alpha equals 0.77. This is 0.4, and when alpha goes to 0, we will get closer to the delta function. So you can see here that if we have the same input from both of the ears, then our threshold will be pretty low. But if we have input only from one ear, then the threshold is high. Okay, and if we check it for different frequencies, then we can see that as higher the frequency gets, then our model is less good. First of all, the neurons get worse in their function. Our neurons in the model can detect less because they are going, the graph going left, and the difference between the dashed line and the point neuron and the bipolar neuron becomes smaller. So the difference between this and this is not as big as the difference between this and this. And they say this can be explained by the jitter. Jitter is when we have a stimulus in a high frequency, then there are some differences in the conductance that are too fast. So there's an overlap between the maximum phase and the opposite phase. There's a leakage to the opposite stage, and then there's still some conductance when there's not supposed to be, because the phase is completely opposite. We can see it here in this point. Okay, so if we have still a little conductance from the right, then the conductance, the input from the left that we need in order to create an action potential is much decreased than the input when we have no conductance from the right. Okay, so when we get to higher frequency, we have some leakage that creates, that makes our dendrites nonlinear explanation to be less effective, and it will come to a point that it will be even worse, even less good than the point neuron. Okay, so I think sorry.
So what was the point? The point was that when you have, they try to explain why for high frequencies,
Yes.
it's a real
So the
neuron.
point was the fact that we talked about in the beginning, that these neurons have long dendrites for the high frequency, for the low frequency, low frequency cells, and the cells that cause the high frequency have short dendrites. So they say if our dendrite formation is advantage, so it happens especially at low frequencies. So we need long dendrites, which makes the formation be more nonlinear. As we get the dendrites smaller, they just get more like a point neuron. Everything is closer to the soma, and the formation is more linearly. And then the decoding is there's this effect is avoided. So they also
there is no, I think maybe it's fine.
Yes, I think
it's too much information. I think even for me, although I review this paper. so the point is that the advantage of dendrite, that you feel the advantage of dendrite when you have a relatively slow input. Then you get this summation and this nonlinearity, and what we said before. Then you can get this suppression, and then dendrites can really better distinguish between the 2 years, so to speak. But when it's high frequency, the dendrites do not have any more an advantage. Sometimes they even corrupt the advantage, and then you would design, as a designer, for high frequency, you would design a point neuron, because it's a waste to have dendrites, so to speak, in terms of speed. So that's how they explain that nature decided that for high frequency, I will do a point neuron, and for low frequency, I will do a bipolar neuron. And for even lower frequency, I will do even a longer neuron. Yes, that's what they try to say. The connection between the structure and the function, because of their model.
Yes. So they use another model later, but to conclude, they showed that nonlinear formation on bipolar dendrites enhance coincident detection, and actually the dendrites can make the neuronal function better.
But only if each year goes to a different dendrite.
Yes.
But that's the amazing thing.
Yes,
the whole system is built that one dendrite listen to 1 year.
No, this is known.
That's known. I'm saying that's a very special system.
Yes. Okay.
A very special mapping.
Okay, but you're leading to the next time. I will just say that they also, like we talked before, explain why there's different dendritic lengths. And of course, the question is this model relevant to other more common cells with other dendritic trees and branches? Because this is a very specific and it's interesting, but can we conclude from this to other mechanisms? Remains question.
Okay. Question?
We have no question.
Thank you. Okay, good.
Maybe a question to you. Was it ever tested if this model is
Actually working.
How can we test it?
I mean, this is quite
This
important.
question has to now really. This question has now to be delivered to a visitor of Eli Melkin, who gave a talk here last Thursday or not this one, but the previous one, because he was the one to do the original work, really the experimental work, not the model. And one way to show it is to record from dendrite. While you get input from different years.
But we know for a fact that dendrites are non-linearly, no? It's not a...
I don't think so.
Oh, okay.
I don't think that
I
they know
thought
that it sounds nonlinear.
This is what I got from your lecture.
No, this is not only nonlinear, it's sublinearly.
Yes.
It has to sublinearly sound. This was never proven. So
okay.
it's a model. So I'm not aware, but I'm not so much into this in particular, if anybody showed that indeed when you activate 1 year, stronger and stronger, you get sublinear summations on different frequencies and so on. That's one way to prove this model. Yes. But I don't know if but he should know. He was really the one to. We really have to discuss it with him. Myself too. But I can't answer this question. No.
What's the time resolution of this conjugate detector?
I don't know. I think it's calculated because
They are very, very good cells. These are the kilohertz. These are very fast
kilohertz.
samples, so that we can really detect small,
in millisecond or in microsecond?
depending on the system, on which animal. But
This is a good example of hyper acuity, where it's microsecond.
Microsecond, yes.
well,
It's
amazing,
amazing system.
amazing system. Okay, maybe. Sorry, there was another question. Okay, so let's take, but not long really, because I really want to finish before 2. So please take a fast drink or something. Yeah, and you can do it.
How much?
Hello?
Yes.
Hello? I presented for graduate school interviews at the LA Fund. In front of all these like really smart people, and I presented something that was really stupid. And let's just say I didn't get the but it wasn't like
What did you present? An article?
I presented my work,
Okay.
which is even worse because like everyone, the most funny thing is that I left out details because it was really working hard. I left out key details so someone else couldn't steal the idea, and they asked about every single detail I left out.
And
And
they
I
stole
told
your
them to.
idea?
Actually, one of the ideas they didn't steal, but it was fine. It was
It's a Nobel Prize winning idea.
no, it wasn't,
Oh.
but it was like a further directions kind of thing, which whatever. I don't have any problem with that because I wasn't gonna do the idea. I mean, the whole point I
Dude, an
presented.
idea is worth its weight in gold.
Not experiments though, because like especially.
A good idea. The world has been shaped by the big ideas. Like guns, germs, and steel.
Yeah.
I haven't read that book yet, but I want to.
I want to make sure this works.
Dink.
כבר יפה.
Dink. 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 Oh!
וואו. Alright.
I'm ready.
All the single ladies. Yeah, count some seconds.
Hey guys.
Lots of stuff.
Hello, hello.
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 Oh god. Wait, did you look at the new neural networks homework?
Hello.
What did it do? Like the ones they after break?
Yeah.
No. Give it some
Hello.
time and do. Or I didn't see what it
Hello.
did. Right.
What? Oh, yeah. Why is it so worrisome?
Because I don't want it to form into a scientific break.
But
Huh.
but
Makes
like
me sad.
okay, we're also gonna do it tomorrow.
What?
Project. Yeah, that doesn't make you feel better. It makes you feel.
Opposite of better.
But it, you wanna let's do it. Start it today.
We have to finish the other one today. Or do we finish it? We'll finish it. We can finish it with what?
We need to
Is
start
there
it. We're not gonna get done. Are you done?
experimental? There are these like great textbooks like that are for like undergraduates only, and it's like they talk about an experiment. It's like cerebellum, versus Sarah, or also like Professor Serotonin. They're so lame, but they're hilarious. That's a good one. All right. Good.
One thing I like about presenting your own work though, you don't have to prepare because you've done it, right?
Yeah, I guess.
Like you don't have to learn like what every little step they took because you took the steps. So if someone asks you like, I don't know a lot of answers to what they did here because
Makes you feel like I don't know any of the questions.
they didn't. No, I'm saying I don't know. Like if you ask me like a specific thing, like how did they
What was the resolution of the
capture a car?
microscopy in the other paper?
No, but like yeah. I presented a lot of papers on my data. Probably presented like 6 papers. So this isn't that bad, but I've never presented a modeling paper. Actually, I have presented modeling. I don't know. Like,
What?
I presented hundreds of times. Not hundreds. I presented a lot in my life. I went to a school in class, and instead of having finals, they had presentations at the end. So you were like, 12, 16-year-old kid. You had to go in front of like
Oh, in high
an
school?
audience, yeah, and like present. I did that.
In college, I had to do a presentation in Chinese for Chinese one. It was so hard. Like the presentations were all the units we did. Like we did a weather unit, a family unit, a sports unit, and like you just give a presentation about food. I'm like, how
20 דקות.
Alright, so I'm going to go fast, so stop me if there's any questions. So the paper, first of all, my name is Benjamin Weiner, and the paper I'm presenting is dendritic integration and its role in computing image velocity. So this paper essentially will present a model, and then we'll test it in a very simple model, the flow slide, but still an interesting model. And this theory...
What's your name again? Sorry.
Benjamin Weiner.
Benjamin?
Weiner, W-E-I-N.
Benjamin.
Okay. This paper is the first to take a theory which is not coming from experimental results and prove it in an experimental system. And to this day it still withstands the test of time. As you can see, it's from 1998. So the methods here are a little rough compared to today's method. And of course, the main theme that we've seen in the past two papers as well is we're going to take some kind of functional interpretation, some computation, and map it onto a morphology, a certain, you could say, geographical arrangement of the neurons, so that we can, just by looking at the dead topograph of the neuron, we can see, or of the system, we can extrapolate a computation from the system. Okay, so I got this idea from Idan. So what are we looking at here? First of all, it's motion detection. And of course, motion can be seen as a very complex thing. We're going to look at it at a very simple level. So response to bars that are moving across the screen, essentially. For this example, the fly is looking at bars moving beneath it. And so it's like this sculpture here where, this is movement of a dancer, but it's only where there's movement that the sculpture is captured. Okay. So, the model that we're going to be testing is called the Reichardt model. This guy right here, which he developed at Max Planck Institute in Germany, along with this guy Hassenstein. You can guess who the biologist was of the team. It's called the Reichardt detector. So Hassenstein was the biologist. Anyway, so before I get into the details, I want to do a quick example because it gets a little tricky. So this makes things a lot easier. We take this very seemingly complex model, and we can represent it here. This is from a Berkeley website, University of California, Berkeley website. And you can see that my mouse, right here, is your moving bar. Okay? And these two big dots are neurons, or whatever you want to call them. And they're going to send some kind of current, or whatever you want to call it, to that bell, which is the soma, or whatever you want to call it, which, if that bell rings, that represents an action potential, or, again, this is just an example. Okay, so you can see if I move, well, first of all, we can play a little game real quick. What do you think the preferred direction of this system will be? Going this way, left to right, or right to left?
We know.
Right, so that's the question. If you see, these are the cables, right, and these are passive cables. And so when something stimulates here, the signal goes along this cable to the soma, the bell, and if it gets enough input, if the bell gets enough input, it will ring, it will have an action potential. So you can see, what direction do you guys think it would be? Left to right, or right to left? Left to right. Right. So you can see, at the correct preferred direction, the correct preferred direction and the correct velocity, it will excite. Now, if you can imagine if it goes faster, doesn't do it, and of course, as you assume, the opposite, the null direction or the non-preferred direction doesn't have any influence. Okay, so that's the model. Is everyone kind of with me so far? Okay. So now here's the actual model, and so you have two photoreceptors, 1 and 2. And these are, of course, arranged in a way such that a moving bar, and of course this is in only one dimension, right? It's going either right to left to right, up to down to up. And so you can see that one photoreceptor receives an input, which then gets filtered, and then by the time that this filtering has happened, the second photoreceptor is also getting input. And both of these inputs influence each other in such a way that this, the two signals will go through a multiplication step, a nonlinear step, which will then cause excitation or inhibition, and that the sum of those excitation and inhibition will be a result. So again, in this particular example, if you hit 1 first, and then you hit 2 at the correct time, so that the signals here match, right, the multiplication step, signals are getting here at the same time, then you'll have the excitation will be greater, and the sum will be a active potential, or a EPSP, or whatever you want to say. In the opposite direction, you'll have more at the inhibition, and so you'll have decrease in an EPSP, or you won't get to a.
So this model, the state cell is all is a excitable and inhibitory?
Yeah, so it's 2 cells, right?
Yes.
And so it's essentially they're hitting, they're interacting with each other to produce either both excitation and inhibition. Okay, and so again, here's you take a step back, and you can see that this system with a bunch of photoreceptors along the axis of movement will result in, if it's in the preferred direction, it will result in what this is, you could say it's EPSP, or action potential here, this is represented here, after the summation. And so the idea here is that this is happening at the dendrite, and that's how we can have motion detection. And so the model we're going to be using, well, first of all, let me mention the prediction power. So from this, and by the way, this is how they originally got the idea for this model, is they recorded from optomotor response from beetles who were taped onto some kind of thing, and they were walking along this maze. Anyway, it's not important. So the idea here in prediction is that you'll have asymmetric temporal filtering. So what does this mean? It means that the response here will be at a different time than you'll have a response here. Okay, and so I should say, and that's represented by this transformation step here. And the second thing that you can predict is a nonlinear interaction stage, right here, this multiplication step. And you can, of course, predict geometric alignment. So again, that this photoreceptor here, will be in the path of the moving bar before this 2, so you'll have an offset there. So these 3 things we can now check in an experimental system. And so we're going to use the fly. This is the blow fly. And you can see that here you have the lobula plate. And it's, I think it's 3 synapses, I'm not totally sure, 3 synapses after the initial retina. Yeah, it's a little complicated here, but essentially here's your lobula plate. And in this lobula plate we have, and what we're going to record from, is tangential cells. Each cell is distinguishable by morphology. We have 2 types, VS cells and HS cells. You can kind of guess from the name that VS is for vertical motion and HS is for horizontal motion. And so what we're going to be looking at as well are not action potentials, but the calcium dynamics that occur through calcium imaging. Okay, so this is how we're going to start with our model. We're going to use a compartmental model, just as we discussed in class. We're going to break down the neurons. So first of all, this paper from 1998, their methods were much more crude. They took a picture, essentially, right, of a neuron that they stained the neuron, and then using light microscopy, looked at the structure, and then attempted to reconstruct it by hand a lot of times. And then from that hand drawing, they would take points along that neuron to get the rough structure, and then each along a certain amount of points, they would have a compartment. And then model the passive membrane properties along each compartment. And so here you can see you have resistance to the membrane, internal resistance, Ri, and you have a membrane capacity. So putting these properties, which were from experimental systems, into this, I guess, a precursor to the neuron program, Mimosys, which then they could run the simulation and see what would come out of that simulation, what they could predict. And again, you have 32, for this particular simulation, they had 32 excitatory and inhibitory correlation type detectors. Correlation type is the same as Reichardt type. And here is a schematic of these simulated detectors. So again, this input right here on the right, and you can see PD motion, preferred direction, right, as Adar talked about. These are the photoreceptors, and then these are the outputs. And these outputs would be synapsing onto the tangential cells, which is what we're recording in this paper. Okay, so again, we predict that there's going to be a low pass filter, some kind of filtering, and then a nonlinear stage. Okay? With me so far, so? Okay. And so now the methods that they used are this fly system. They have just a normal kind of CCD camera. They're recording calcium concentrations, and so they're using something called calcium green. They take a frame for reference, and then every frame after that, where they're looking for the signal, they subtract the reference frame from that signal. So it's a way to look at how calcium is changing. And again, like I was saying, there's a translucent screen where there are moving bars, and of course they can change the direction, or they can also change the velocity. Okay. So the small question I have to ask, I'm going to skip right through. Does intercellular calcium increase in response to preferred velocity? And they show this because they have to make sure, and this is a little old, shows the age of the paper, is that they have to show that membrane potential in the neuron is correlated to changes in intracellular calcium levels, because they're, of course, measuring calcium, so they want to make sure that's right. And so the answer to the question is yes. Okay, and let me just show you a couple examples of the kind of results you can get. So this is when the cell is stimulated. This is when the fly is shown motion in its preferred direction at a velocity that's also preferred, and you can see that there's an increase in the calcium concentration along the dendrites. So you can see this is kind of where the soma would be, and you can see the axon kind of lightly. So you can see that when you have an increase in calcium, there is a preferred direction motion, and the opposite is true when there's a null direction or anti-preferred direction stimulation. You see that there's a decrease in the calcium level throughout the neuron. Okay, and again, these pictures are quite yeah.
Do you know what the dot?
Yeah. So I'll get this dot right here.
No, the bright spot.
Right here. Yeah, so this shows how their methods are somewhat crude, right? Because you're taking a very noisy image, and of course this is using light microscopy. Now people use two-photon imaging, like Michal was talking about, to get very, very high resolution comparatively. Okay, and so this can be quantified, and you can see it here. Again, this is in comparison to the reference frame, right? Because there's always calcium going around, obviously, throughout the cell. And so when you show preferred direction motion, you have a nice increase. And then of course, after you stop showing preferred motion, you have a decrease and back to normal. And then once you show null direction, right, the opposite direction, you have actually a decrease in the calcium in the cell, which then returns to normal. And here, this is actually recording from the soma. And you can see the same membrane potential. And I should say one little thing is that these spikes are irregular. And they are above, obviously, the normal amplitude of the cell, normal voltage of the cell. So this is what they call a constant shift. Where even though there's action potentials here, what's more interesting is the constant shift of the baseline in the preferred direction. Okay. Okay, still with me? Okay. So the first actual question they ask is, what does the simulations predict for dendritic membrane potential? So now, I kind of already spoiled the surprise, but now I'm going to show you what the model predicted. Okay? Exactly what kind of activity would you predict for calcium at these per calcium signal at these dendrites and at the axon. And again, this is using so you can imagine each one of these parts is a little compartment where they're calculating the passive membrane properties. And so you can see that these are 1, 2, 3 different dendrites, and these are the corresponding signals from the dendrites, the voltages. And so you can see that each one of these signals has a peaks at different times, right? So there's a temporal offset, and you can see there's a constant shift, meaning there's a constant increase in the baseline voltage. And on the other hand, at the axon in 4, you can see that there is a constant shift, but there's no temporal offset. The axon has a relatively smooth increase in voltage. Okay, so this is what we threw in correlation type detectors, and we attached them onto this compartmental model, and this is the result that came out. Okay, so now we're going to check this simulation to the actual experimental data, which we can record. Yeah.
Obama McGee.
Yes. Hopefully it's coming. Hopefully he'll stop by.
It's the American helicopter. כן, זה נכון.
הוא לא לבד.
They're landing in Costa. Next to the swimming ship. Sorry.
No. It's Obama. Okay, so the major question of this paper, and the one I can spend the most time on, is that do local inputs to these lobular plate tangential cells exhibit Reichard detector properties? So if this is true, then we can show in a real physical system that the model that Reichard developed in the 50s, but forget this, all the way back from the 50s, is true. Okay? So first of all, we look at constant motion response. So this is not changing velocity, but in the cell's preferred direction, right? And so you can look at different. So again, we can all see this is the axon, these are the dendrites, and so we're going to look at calcium in these specific spots that are, of course, different in their spatial property, right? There's one here, and of course in their temporal properties, because the input from the eyes is getting there at different times. Okay? And so from this picture you can't really see anything, so we're going to quantify it again. So now you can see that, again, this is just to make sure everyone follows, this is 1, 2, 3, 4, right? Different in spatio-temporal properties, and then 5 is your axon. So you can see that 1, 2, 3, 4 all seem to be having constant motion, meaning constant shift, meaning that they're getting their voltage is consistently increased, or their calcium levels in this case. And you can see that there's a slight shift, right, in their response phase. So I just did a little bar right where one of the peaks are, and you can see that the bars are roughly different from each other. And again, this is something that you would need for the Reichard model to work, and this is something also you expected from the simulation. And of course, 5, you're seeing that despite this noisy, corrupted is what they call it, inputs in the dendrites, somehow you're getting a relatively flat response in the axon. And of course, this is just recording from the soma, which is showing, as expected, a constant motion, constant increase in voltage. Okay. And so now, again, we can go back really quick and compare it to the simulations, and you can see it's almost perfectly aligned, except for there's a little more noise in the axon in the simulation than predicted. I'm not sure why. And I can even put them right on top of each other, and you can see almost perfect matching. Okay, so the last question is, how is local calcium activity modulated in the dendrite? Because it could be that the calcium activity that we're seeing is coming from the postsynaptic, the cell we're actually recording from, or it's calcium level increasing in the presynaptic cell, because as we know that when there's neurotransmitter release, there's also increase in calcium, et cetera, et cetera. So this is a smaller question, but what we wanted to test is whether voltage-gated channels are necessary to see this effect, because if voltage-gated channels are not necessary, then we can just assume that it's some kind of gated channel that's causing it. So, yeah.
For the previous
Yeah.
slide, I
So,
don't
this
want to you or maybe to Jan. I wonder how can you quantify, let's say, for the right, the lower one, the black one?
Yeah.
How can you quantify the differences that we're giving? You said it's a bit different. That we can see it in the eye that it's a bit different, but I wonder if there is a way to quantify, to experimentally to see if this difference is crucial maybe. I mean, it looks small, but small is relative.
Right, so we could probably maybe change either some parameters in the model, I was thinking, that would maybe, make it a little less noisy. But one thing I should say is this is not really that quantitative of a proof that saying that the model is the same. So this, just like all these that I've been showing, I should say this one, this is a VS stuff, but all these pictures are not really quantified that, and that's one of my criticisms about the paper, is that, and it is a science paper, I should say, but is that the experiments are kind of not right. They're qualitative in a way. There is some quantification in the paper, but it's a little complicated. And it's not like there's no comparative statistics used in this paper. Okay. So now we can check for how voltage-gated channels are involved in this result we're seeing. And so we can test that very easily by just sending a current ramp, right? Doing a current clamp, sending a current to minus 14 nanoamps, and that will cause voltage-gated channels to close and not to respond when you're showing motion in the preferred direction. And this, of course, is a horizontal. I should say this is a horizontal cell. Probably you can see kind of the morphology is different. So again, we're recording from the soma, and we're going to close up on the axon and on the dendrites. And so again, if voltage-gated channels are necessary for this result, then if you block them, you should see complete abolishment of the result. Whereas if they're not involved, then we should see that the result still stands. On the other hand, we see, and you can assume, and you could have guessed, is that these voltage-gated channels are involved, and once you block them, you see the response is abolished. You even see hyperpolarization until you stop the current clamp back to the original level. Okay. So from this you can say that these what they're called voltage-activated calcium channels, these are driving this calcium response. So this means that we're looking at a phenomenon that's happening in the tangential cell, not something that is a result of presynaptic input. I mean, obviously the presynaptic input is involved, but it's both at the same time. Okay, so the key here is, again, function to morphology. So we found some function. We saw this constant increase in the current, in the voltage, we saw this constant increase in the voltage, and we saw a temporal delay. These two things, which are shown in and again, this is all calcium modulations, which we can assume reflect local dendritic membrane potential modulations. So you can see that this all would have to depend on geometry, because the stimulation would have to arrive at both the correct velocity and the correct direction in order to, again, let me actually go back to this. you would have to have your photoreceptors in the correct morphological order in order for you to have that temporal offset, and that is allowing you to distinguish the motion. So the idea here is that if you look at the system and you only knew the morphology, you could assume the function just by seeing that it's receiving inputs in a retinotopic way, and by that you can assume what its computation is doing. Okay, and so the last slide just is that my impression of the paper is, again, it's very quantitative. At one point they say they did further 10 experiments to confirm this effect, but didn't specify what they were. And nowadays, but of course with time this has been shown to be true, and nowadays there's a model fly project which is looking at neurons in even more detail in the fly, and again using the same kind of modeling but with better data to further prove their original theories and possibly try to assert theories about different types of visual properties of the world. And my only criticism is whether there are further conditions. So whether that the model is capturing everything, because for example there could be a condition where there's too much saturation. One of those filters could have some frequency in it that is too high, and then how would that affect the system? That isn't captured in the model. So that's my one major criticism that could of course be solved by adding further conditions to the model. So that's the paper.
One quick question, because so how did they show that it work? So you look at, let's say, vertical cell. What makes it sensitive to vertical direction or horizontal? We did not understand from this what makes this cell directional selective.
They didn't show.
What is the computation that the dendrites are doing, particularly to make this cell sensitive to this direction?
Well, first of all, they didn't specify which which specific cells are
But
the input.
a given cell that is directional selective, let's say horizontal. What is the origin of this directional selectivity?
Right. So they're receiving retinotopic input.
Okay.
Right. So the real question is what is happening at the dendrite to have that spatial integration.
So how does it become horizontal direction?
No,
So they don't answer this question.
No.
So the role of dendrites here, in some sense, as I understood what you said, and I know this paper also, that the fact that what the dendrites are doing here is averaging out local noise. Yes, because you see the modulation of the input at each location, so it does like noisy thing in the dendrites. But at the soma, not knowing why it is directional selected to this direction or another, the role of dendrites is to smooth local perturbation or local noise and make the output smoother, just because they smooth the end. So that's a role of dendrites. In this case, dendrites are for what they show. I don't say that this is the role of dendrites, but what they show is just dendrites are smoothing local noise. And eventually in the cell body you see something smooth. And in the dendrite you see something noisy.
Right, because
that's what they showed.
Right.
They didn't explain anything about
If I'm correct in this, is that the dendrites would be at this summation step, correct?
Yes,
In this model.
but the computation was not shown. It just shows the smoothing.